Okay, so thank you. So, good morning, everyone. So today I'm going to talk about partitioning via cluster graphs, and I'm going to talk about spectral clustering. And this is joint work with Richard Peng from Georgia Tech and Luca Zanetti, who's my PhD student at Bristol. So in this talk, we look at very basic question. So assume that we have a large graph, and this graph consists of a few clusters, and vertices inside cluster are highly connected. Only a few connections between different clusters. We want to approximately recover all the clusters. So this problem appears in many areas in CS, like machine learning, image segmentation, and the analysis of social networks. So around 25 years ago, spectral clustering was proposed, and this can be summarized as the following three simple steps. For simplicity, we only assume that L is a normalized Laplace matrix of G, and I will define L formally later. So we assume that lambda 1 to lambda n are the eigenvalues of matrix L with the corresponding eigenvectors f1 to fn. So with this, the first step is to invite every vertex of G to a point in k-dimension space according to bottom k eigenvectors. So now we have k endpoints in k-dimension space. We simply apply k-means algorithm to group the n vertices into k clusters. According to the outcome of this k-means algorithm, we partition graph G into k clusters. So it's clear?
We don't know what the k-means algorithm is.
Yeah, I will discuss later. Okay, so these are very simple three steps. So the question is, can we analyze this framework theoretically? So in this talk, I will show that spectral clustering works for large family graphs, and this great extends the previous work with only false for graphs generated from stochastic block models. Okay. So here is the outline of the talk. We first introduce some basic notations, and I will analyze spectral clustering algorithm. And for the third part of the talk, I will present a linear time algorithm for partition graphs, and you will see that we can partition graph as fast as the time required to read the whole graph. Okay, let's start with a basic definition. So in this talk, we assume that G is an undirected graph with n vertices and m edges. So we use L to define the normalized Laplacian matrix, where L is defined as the identity minus inverse of D times A. Here A is the adjacency matrix of graph G, and D is a diagonal matrix consisting of the degrees of vertices in G. For example, so this is a 4-vertex graph, and every vertex has degree 3. So this is the corresponding normalized Laplace matrix. So for all the diagonal entry of this matrix is equal to 1, and since every vertex has 3 neighbors, so all the off-diagonal entry equals to minus 1 over 3. So as you see here, so the normalized Laplace matrix is real and symmetric. Therefore, this matrix has n real-valued eigenvalues. We call it lambda 1 to lambda n with the corresponding eigenvectors f1 to fn. So now we need to introduce notion of graph conductance in order to formalize notion of clusters. We first introduce the conductance of set I, which is defined to be the number of edges between set I to the complement of set I divided by the volume of set I, because volume of I is the number of edges adjacent to vertices in set I. So we also introduce notion of conductance of graph G, which is the minimum of the conductance of set I over all possible subset I, whose volume is at most the volume of G divided by 2. So this conductance of G captures the sparsity cut of graph G. So in general, computing the conductance of graph G is NP hard. So however, the very famous triggering quantity states that conductance of G, this phi G, can be approximated with respect to the second smallest eigenvalue of the normalized Laplace matrix. So now we generalize the notion of graph conductance to the K subset case. We introduce the notion of K-way expansion. So assume that we want to partition graph G into K clusters. So we look at all the partitions A1 to AK, where for each partition, we look at the maximum of the conductance of AI. And rho K is defined as the minimum of such value over all possible partitions. So it's easy to see if graph has K clusters, which means we can partition graph G into K subset such that every phi G of AI is small. In this case, we know rho of K is small as well. So recently, Lee, Oris, Graham, and Trevisan show that actually we can have similar, the behavior of rho K is very similar with the standard case of graph conductance. So namely, we can approximate rho K with respect to lambda K as well. Okay. So let's look at this high-order trigger inequality for a while and see what it tells us. So let's assume we are at a situation for which rho K is small and lambda of K plus 1 is big. So by the standard high-order trigger inequality, we know that since lambda K plus 1 is big, rho K plus 1 is big as well. Okay. So because the value of rho K is small, we know that we can always partition graph G into K clusters, for which every cluster has low conductance. However, if the value of lambda K plus 1 is big, we know that no matter how we partition graph G into K plus 1 clusters, there's always a subset with high conductance. So this means, assume that we have a large gap between lambda K plus 1 and rho K we call epsilon. This implies our underlying graph G has exactly K clusters. This is our key observation. So in the following of the talk, we simply use epsilon to define the ratio between lambda K plus 1 and rho K. And actually, we'll show that once we define we condition on this epsilon, this gives us a lot of useful properties. So our first result is called the structural theorem. And let's look at the structural theorem informally first. So let's look at a tall example. Assume that our underlying graph G is a D-regular graph with K entirely disconnected components. For every subset Si, we define the indicator vector of Si, we call it Gi. So G of U equals 1 if U belongs to Si. Otherwise, G of U equals to 0. Okay. So remember, this is a combinatorial properties of the clusters, right? So now we further notice that F1 to Fk are the eigenvectors of the graph. Okay. So in this case, it's easy to prove that the set of F1 to Sk equals to set of G1 to Jk. Okay. These K vectors are exactly the same. It's not surprising at all. So, but what does it mean? This means if we apply the spectral embedding, these K vertices are mapped to K disjoint points, right? Which also means vertices map to the same point if and only if they belong to the same cluster. So what we are going to prove informally is assume that we have a gap epsilon is at least K squared. Then we look at the space spanned by F1 to Fk. This space is approximately equal to space spanned by G1 to Jk. What does it mean? Let's look at a formal version of the structural theorem. So we have two sets of vectors. We have F1 to Fk, which is the eigenvectors of the normalized Laplace matrix. We also have Gi bar. Here is some normalized eigenvector of set Si with some proper normalization. I will skip the definition here. So we can prove the relations between Fi to Gm from two ways. First of all, we show that for every Gi bar, we can always get Fi height, which is a linear combination of the bottom K eigenvectors such that we can list L2 the square distance between F1 height and GA bar is can be upper bounded by some factor inversely proportional to epsilon. So this is was already shown in the very famous paper by Aurora et al. Around 6 years ago. Okay. So more interestingly, we can show the other direction as well. So namely, for every Fi, we can find GN height, which is a linear combination of the normalized indicator vector, such that the L2 square distance between Fi and GN height can be upper bounded with respect to epsilon as well. Okay. So there are a few interesting consequences of this structural theorem. But one consequence is, remember, we define FU is our favorite spectral embedding used in spectral clustering algorithm. So once we use spectral embedding to map every vertex to a point in k-dimension space, we are able to prove that there always exist k points, p1 to pk, such that also embedded points from cluster Si is concentrated around Pi. This is crucial thing used to analyze the spectral clustering algorithm. Okay. So now we go to the second step to analyze the spectral clustering algorithm. And we first recall what is k-means clustering. So this is well-studied combinatorial optimization problem, and which was introduced around 1950s. So the problem is as follows. We have a set of n points, x1 to xn, where every point xi is in d-dimension space. We also give a parameter k, which is a set, which is number of clusters. So now we want to group these n points into k clusters, such that the following objective function is minimized. So we want to assign every point x to a cluster xi, and for each cluster Si, we want to find the center Ci, such that if you look at the total L2 square distance between all the points x to his corresponding center, this objective function is minimized. Okay. So just remember, this is the objective function we use when applying the k-means algorithm. So based on the structural theorem, we are able to prove the following facts. So first of all, we look at the embedded points Fu and his approximate center Pi, and we can bound the total L2 square distance can be upper bounded by k squared divided by epsilon. Remember, epsilon is a gap we introduced in the first part. This shows that once we have large value of epsilon, all the embedded points are more concentrated around his center here. Secondly, if you look at the distance between different clusters, this distance is inversely proportional to the volume of the smaller cluster. This shows that if we have large cluster and we have smaller cluster, that a smaller cluster is far from any big cluster. This is crucial in analyzing k-means algorithm, because otherwise, this also shows that a misclassification of smaller cluster will introduce a lot of error to the large cluster. And this is very crucial in analyzing the spectral clustering algorithm. A third step, which is quite surprising, is if we look at the large cluster and smaller cluster, so the bigger cluster is always closer to origin, and smaller cluster is far from the origin. Okay. So this is based on the structural theorem. We can prove the lithostrip properties. And actually, lithostrip properties suffice to analyze spectral clustering algorithm. So here is our result. Assume that we have gap epsilon, which is at least k3. If k is a constant, we assume that epsilon is large constant. So A1 to AK is the output of spectral clustering algorithm. And the corresponding optimal cluster of AI is Si. So our first result is the volume of the symmetric difference between Si and AI. this measures the misclassified part. We can show that volume of AI and Si is at most k cubed volume of Si divided by epsilon. This also shows that once we have large gap of epsilon, the spectral clustering performs better. Secondly, if you look at conductance of every return AI, this can be upper bounded with respect to the conductance of Si as well. So now we go to the third part, and I'm going to present a linear time algorithm for partitioning graph. Let's first recall our current situation. We want to partition graph G into k clusters. In order to do so, we apply two steps. The first step is to map every vertex to a point in k-dimension space. We need to compute the bottom k eigenvectors of the normalized Laplace matrix, and this takes time at least m times k. Secondly, we need to apply k-means algorithms in a geometric setting, and this k-means algorithm runs in at least n times k time. So as you see here, for small value of k, for instance, if k is 3 or 4, this two approach implies linear time algorithm. However, for large value of k, for instance, if k equals to square root of n, these two approach run slowly. So in order to get linear time algorithm, we need to break these two barriers. In order to break the first barrier, we need to approximate the spectral embedding without computing the eigenvectors. In order to break the first barrier, we need to speed up k-means for our specific setting. And let's break these two barriers one by one. So for the spectral embedding part, so if you look at k-means algorithm, actually you will see that we only need to approximate the distance of the, we only need to approximate the L2 squared distance of all the embedded points, Fu and F3, instead of using the closed form of the spectral embedding for every vertex U. So the first result, we are able to prove that actually in linear time, we can compute an embedding XU such that if you look at L2 squared distance between all the embedded points using the embedding X, this gives a pretty good approximation of the spectral embedding up to a constant factor. So now I won't discuss the details about how to obtain the embedding, but let's assume that we have this embedding for free. And let's see how to speed up the k-means algorithm. Okay, so now our algorithm framework consists of 3 steps. The first step is very easy. We sample k log k vertices, and every vertex U is sampled with probability proportional to degree of U times the norm of Fu squared. So why is this the case? Just remember what we proved is also embedded points is close to his center Pi. And the L2 squared distance of Pi is inversely proportional to volume of Si, right? So now if we sample every vertex U with probability proportional to du times Fu squared, this guarantees that basically every class will be sampled with approximately the same probability, right? Because the total probability mass to sample each cluster is sum of the du times Fu squared. And the Pi squared is inversely proportional to volume of Si. So now by the standard coupon collector argument, we know that after we sample k times log k vertices, so with constant probability, every cluster has at least one vertex sampled. This step is very easy. So we need to partition the vertex set into k clusters. So now we have k log k vertices. So the second step, we just delete the points in the sample set which are far from each other until there's exactly k vertices left. We can prove that with constant probability, every cluster has exactly one vertex remaining in this sample set. Okay. Now for the final step, so for all the remaining n minus k vertices, so every vertex simply find his closest neighbor in C. So and with the third step, we can use approximate nearest neighborhood data structures. And the third step runs in linear time as well. So combining these three steps, we show that actually we can, for clustering graphs, we present a linear time algorithm because all these three steps runs in linear time, and it shows that actually we can partition graph almost as fast as we read the entire graph. Okay. So now let's summarize what we discussed so far. So we present our first result is a structural theorem. This gives a close connection between the eigenvectors of matrix and the cut structures of graph. And our structural theorem can be viewed as a stronger version of the well-known Davis-Kant theorem, which is a very classical result from operator theory. So secondly, we present theoretical analysis of spectral clustering, and we show why spectral clustering works for large family of graphs. And previous to our result, most analysis only holds for graphs generated from stochastic block model. So our third result is a linear time algorithm for partitioning graph, and our result rigs random vary omega mk for spectral clustering algorithm. And for a few aspects for k-means in the classroom, you'll see that actually our result shows that actually the classic lower step heuristic for k-means algorithm can be eventually avoided for certain cases. That's the end of my talk. Thank you.
Questions?
Yeah, here, a crucial assumption here is you know K, right? So
Yes,
in
we know
practice,
K.
how do you choose K?
This is a very good question, and I think this is a large research topic. There's a lot of reference only focusing on how to choose the right value of K. But here is we assume that K is a part of the input.
So I don't have a strong intuition of how clustered a graph needs to be for your bound on epsilon to hold. So although I know you're trying to get away from the stochastic block model, which I think is great. In that model, I mean, does your bound apply anywhere near the known transition and community detection, or?
For many choices of parameters in the stochastic block model, this gives a bound, gives a lower bound of epsilon. But it's hard to give a clear comparison that for certain value of epsilon, this covers all the range of graphs generated from stochastic block model. So I think there's no clear comparison here.
I mean, have you computed epsilon for various benchmark graphs that people enjoy clustering to see if your bounds hold for them, or?
No, but we know that, for instance, if every cluster is a spandrel graph and connected by a few edges, and you can clearly see that in this case, our algorithm spectral clustering gives a constant factor approximation of the optimal clustering with respect to the conductance of each subset.
Yeah, so if you apply your linear time algorithm to a graph that isn't well clustered, where there isn't any clear clustering structure, will the performance degrade substantially, or will there be any sort of indication that you should maybe use the more computationally intensive clustering algorithm instead?
We didn't try that at all. Yeah.
So, okay.
Also, if the graph is not well clustered, you can imagine all the embedded points are not clearly separated.
Right.
And you cannot apply this nearest neighborhood data structures anymore.
Well, your algorithm will run.
Yeah, the algorithm will run, but we don't know the
something.
performance. Yeah, the algorithm will run. Yeah.
And will there be any like alarm that goes off when this happens in the algorithm?
So actually, we don't know in this case if the algorithm will run. No, the algorithm will run, but we can sample k log k vertices, right? But in this case, there's a case probably all the embedded, the pairwise distance of these k log k vertices will be close to each other, right? Then we don't know which point we'll delete. There's no clear separation between the distance of the embedded points within a cluster and from different clusters. So we not guarantee that after the second step, so we get the k vertices. Yeah.